Another consequence of the Baire category theorem is the open mapping theorem. So for this, we now have two Banach spaces, X and Y, and a bounded linear operator, say T, from X to Y. Then T is open if and only if there exists a delta greater than 0. I should say T is open if and only if T is surjective. So for Banach spaces, surjectivity and openness for bounded linear operators are equivalent. And by the way, what do we mean by an open map? So that is if I have a set O in X, which is open. Let's say if O is open in X, then the image is open in Y. So an open map is a mapping that sends open sets in the domain to open sets in the codomain. Well, to prove this theorem, let us consider a simplified version. So let us copy the assumptions of the open mapping theorem. That is, we have X and Y as Banach spaces and T a bounded linear operator from X to Y. Then T is open if and only if the image of the unit ball in X, unit open ball in X, contains an open unit ball in Y. More precisely, there is a delta greater than 0 such that this open ball in Y with radius delta is a subset of the image of the unit open ball in X. And we will see later that this will imply the open mapping theorem via translation, scaling, and among other things. So let us look at the proof of this lemma. So for this, suppose T is open. Therefore, the set or the image set is open in Y. Since, take note, this is open in X. And take note that 0, this is the 0 element in Y, T of 0, the 0 element in X, is an element of this image. So we have an open set containing the origin or the 0 vector in Y by the definition of the metric topology. We can find a delta greater than 0 such that the ball centered at this 0 here in Y with radius delta is a subset of this open set. And this is what we wanted to have. So that's the easy direction. The reverse direction can be established by scaling and translation. So here, suppose that we have this condition. Okay. So to show that T is open, so let us consider O to be an open set. Since the image of the empty set is empty, and that is obviously open, it is enough to consider that O is non-empty. And let us take an element Y in the image. Since O is non-empty, then T of O is also non-empty, so we can pick an element Y. So the goal is to find an open ball that is contained in this image. So by the definition of an image set, there is an X in O such that Y is equal to T of X. Since O is open, X is in O for some epsilon greater than 0. The open ball centered at X with radius epsilon, capital X, is contained in O. From this, we can see that the open ball in Y, having center at Y, with radius, let's say, delta epsilon. Okay. What is this delta? This delta is the number corresponding to this statement here. You can write this as a Y plus, or you can translate, okay? So this is a set where it has the form Y plus X, or I should say Y plus Z, such that Z is in by 0 delta epsilon. Okay, so this is how we define a vector and a set. So it is also a set. Okay, and this is the same as since Y is Tx. Okay, and by scaling, this is equal to epsilon by 0 delta. Again, this set here is defined to be epsilon, let's say W, wherein W is in this open ball. So you scale each element of the open ball. Okay, now according to this inclusion here, okay, applied to this is a subset of T of X plus epsilon T of the unit open ball in X. And this scalar times the set, the image set is defined analogously as before. And you can show that this is T of X plus epsilon Bx. Okay. And this is the same as the open ball centered at x with radius epsilon. Since you have this, so therefore this is a subset of T of O. So therefore, any element y in the image set, you can find a ball centered at that point y that lies entirely also in the image set. So since y is arbitrary, and this implies that T of O is open in Y. And this is true for any non-empty open set in X. The case of O being empty is trivial, therefore T is open. Okay, so this is an alternative characterization of open mapping, of an open mapping between Banach spaces. So for a bounded linear operator, that operator is open if and only if the image of the unit ball in X contains a ball in Y with a center as 0. So let us now, with this, we can now prove the open mapping theorem. So for this direction, suppose that T is surjective. We wish to show that it is onto. Okay, so this part is the straightforward part, since Y can be written as this one. So where delta be the number in the previous lemma. So here we need to reverse the direction. The assumption in the previous lemma is that T is open. Okay. So again, suppose T is open, and then according to the previous lemma, we have a delta such that this open ball lies in this image set. Okay, so this is the same as the union of these scaled open balls. And this is a subset of the union what's this? K times T Bx. You apply the linearity, okay, of your t. So this is epsilon bx, but that would be now the, or I should say, you put k, therefore the radius now here is k. Properties of images implies that we have this. So the image of the union is the union of the image. And for this is what? The same as t of x. Because the union of these open balls for a k from 1 to infinity is the whole space x. And we know that the image set is a subset of the codomain. Thus, all of this must be equal. And so the image of T is just the codomain. T is surjective. Okay, so for this, we have openness implying surjectivity. So let us now go with the previous or the reverse direction. So suppose that T is surjective. And for this part, we consider several steps. The first one, we claim that there exists some number xc positive such that the ball centered at xc centered at 0 with radius xc is a subset of the closure of this unit ball. Okay, and let us define this to be C sub, I should say, let C sub k be equal to the closure of the same ball, but now with a larger radius k. So here we are aiming to apply the previous lemma as well. Now, since T is surjective, Y can be written as the union of this C subcase. Well, what you can do is, of course, these are all valid if you replace this by the closure. That is basically C sub k. So applying the same argument as before, namely this one, you can have this equality here. So we will not repeat that process. Nevertheless, the Baire category theorem, or more precisely, its corollary, since Y is a Banach space, therefore it's a complete metric space, we can find some index j such that the interior of Cj is not empty. Then, from this, we can find an element y naught in Y, or if you like, in Cj, the interior of Cj, which is a subset of Y, and a positive epsilon greater than 0, such that the ball centered at y naught with radius epsilon is contained in this open set, namely the interior of C sub j. And since the interior is a subset of the set, we have this. Since since t is again a surjective, let x naught be in x be such that y naught is equal to the x naught. So again, we apply the surjectivity of t. So let us assume that I have an element in this ball centered at 0 with radius epsilon. Then, let us translate this into y naught. So now the center would be in y naught, so that this translation is an element of Cj, according to this inclusion here. Okay. Since Cj, so let us here recall the definition of Cj. So this is the image of this. According to the definition of the closure, this vector here must be a limit point of this image set. Then there exists a sequence, let's say a yn, and from 1 to infinity, in this image set in such a way that yn tends to y plus y naught in the topology of y. Of course, as n tends to infinity. For each n, there exists x sub n in the ball centered at 0 with radius j, such that t of xn is equal to yn. That is due to the fact that yn is in this image set. So yn must be the image of some element of the ball B0J. And from this, we can now write this as follows. So t of xn tends to y plus what is x naught? Or y naught. So y naught is equal to t of x naught. Okay. So estimating the norm of the following. So let us first take this difference divided by something, So that let us skip first the denominator. So if we apply the triangle inequality, okay, divided by whatever the denominator, okay. The goal here is I want that to be this to be less than 1. So what would be the denominator? Of course, we cannot do anything here. Okay. Take note that xn lies in this ball, so therefore the norm is less than j. Okay. So if I divide this by j plus the norm of x naught, then clearly this fraction here is less than 1. So that would be the denominator here as well. Okay, so we force this to be in the unit open ball in X. Okay. Now that image or the image of this vector here applying the linearity okay, this tends to so we have here, okay, you subtract tx naught both sides, or you transfer this to the right. The numerator converges to y, and you just divide the denominator. So this is convergence in the topology of y as n tends to infinity. Okay, so let us summarize what we have done here. So let us highlight that, assuming we have y in b y naught. This part here and take note that this is an element of C sub j. Okay, why? Since this is so this image is now an element of T of bx 0, 1. And okay, so going back to what we have here. So it's not C sub j, but C sub 1. Since C sub 1, recall that this is a subset of, or it is equal to the image of the closed unit ball and taking its closure. Okay, so in other words, you have a sequence in this image set, and this is a limit. Since the C1 is closed, therefore the limit must be in C1. Okay, so let us summarize that one. Thus, y in the open ball, okay, implies that this y over j plus the norm of x naught is in C1. Now we can choose our number xi to be epsilon over this denominator, which is obviously positive. Going back to our claim, okay, so we want to prove this, and let us note that this is the same as C1 by definition. So pick a point here, we need to show that it's also here. So let's do that. So take an element as Z in this ball. Then if I scale this so that I have this open ball, so what we do is we multiply by epsilon and divide by xc. So we end with the following. So now this will have a radius epsilon. And now so if I have an element of this ball dividing by this quantity gives me an element of C1. So divide that by j plus this norm. Okay, this is an element of C1, but let us rewrite this as epsilon z over c minus j. Okay, the way c is chosen was that this is a reciprocal of c. So therefore, this is the same as z, which is in C1. So given any element in this ball, we also have that element to be in C1. Okay, so let us summarize that one for convenience. Therefore, this ball is a subset of C1, and we know that this is equal to this set by definition. So that's the first step. Now, for the second step, we claim that the ball centered at this is a subset of let us divide this by 2. So this is a subset of the right-hand side, but now without the closure. So here we reduced the ball or the radius of the ball so that we are in the subset of the image of the open ball bx01 without the closure. By scaling, take note that this implies by multiplying by 2, or I should say this is equivalent to the following: by c subset of what t bx 02. Now, from the claim, from this claim and the previous lemma, with delta to be xi over 2, we deduce that T is open. So this is your delta, okay? And if you can recall our previous lemma, this will imply that T is open. Okay, so it's enough to show this inclusion, or equivalently by multiplying to both sides this one. And this is done by a pick a point method. So let's pick an element on the smaller set. We wish to show that this is also an element of the larger set. Okay, according to this first step, namely the one here, stated here. So from step 1, y must be in this closed unit ball, or the closure of the image of the open unit ball. Hence, we can find an xn in the open ball for all n, such that the image tends to y in the topology of y as n goes to infinity. The definition of convergence, so there exists an n such that the norm of the difference is less than xi over 2. Here, xi is positive, as long as the index is larger or equal to this index capital N. Multiplying by 2 both sides, this implies that 2y minus txn is an element of what? The ball in y with a radius c. So here we multiply by 2. And let's pick one index, and that's capital N. So therefore, we have established the following. So for each, or given a y, and this to exist an x, that is namely x of n, in the unit ball such that 2y t of x is in the same ball, open ball. So here, take x to be x of n in the above construction. So we started with some element of this open ball. If you perform this operation where x is in this ball, you end up with the same open ball. So this introduces a recursion. So namely, let us define y naught to be y, which is an element of this ball. We fix this, and for n greater or equal to 1, let us define y n to be 2 times y minus t of, let's say, yn minus 1 minus t of xn minus 1 with xn and from what? And from 0 to infinity. This is what? A subset of the unit ball in x. And this sequence yn, as we know, lies in the ball centered at y with radius c. So you just repeat this process here. So you start with y, and then rename that as y naught. The corresponding x here will be denoted by x naught, and this vector will be denoted by y1. And then you repeat the process. So we have this recursion, and according to this statement here, the y sub n's belong to the open ball in y centered at 0 with radius c. Consider the set of partial sums, say Sm. This is x sub n, and from 1 and from 0 to small m for, let's say, m greater or equal to 0. Okay, so from this, you can show that there's a missing denominator, 2 to the n. Then, this is Cauchy. In, let's say, in x. Well, you can easily see that. So this is less or equal to, so let's say m is greater than k. Here we need to take the sum from k plus 1 to m, okay, of the norm of x sub n over 2 to the n x being in the unit ball, so this is less than 1 over 2 to the n. That's the reason why we divided by 2 to the n, since this will tend to 0 as m and k tends to infinity. So indeed, Sm, the sequence of partial sums, well, divided by 2 to the n, is a Cauchy in x. And by completeness, so there exists x in capital X such that Sm, S sub m tends to x in capital X as m tends to infinity. Okay, Moreover, if we take the norm, okay, we apply the triangle inequality. So here we separated the case for x naught, okay, to the n. This is now what? Again, this is less than 1. So this is less than the norm of x plus. So here you have a geometric series. And this is only a partial sum. And take note that the sum is 1. This is, of course, less than 2. Since x naught is also as norm less than 1. Okay. So if we pass m to infinity here, what we have is that the norm of the limit, which is x, is less or equal to 2. In other words, x is in this ball. So the radius is now 2. On the other hand, if we take the image of this sum S sub m by the linearity of S sub m divided by 2n, this is equal to so we need to go back with the definition. So here you divide by 2 and then change the index n to n plus 1. Okay, you can see that this with n replaced by n plus 1 is the same as yn minus yn plus 1 divided by 2. So you follow the recursion. So definition of yn. We can write this as follows. So yn 2 to the n minus yn plus 1 2 to the n plus 1. And now we have a telescoping sum, and this will be, okay, if you sum this, you end up with y naught minus y n plus 1 over 2 to the n plus 1. This tends to y naught in the topology of y as m goes to infinity, since the numerator, okay, is bounded. Namely, this is less than or equal to xi for all m. And why is that? Because the way we constructed our recursive, or our sequence yn. Okay, so the norm, the numerator is bounded. 2 to the n plus 1 tends to, or the reciprocal of that tends to 0. Therefore, this tends to y naught. By continuity of t, tsm must converge to t. Take note that sm tends to x, so this must be tx in y as m tends to infinity. Therefore, uniqueness of limits. Here we calculated the limit of tsm to be y naught, and here invoking continuity, we have another limit. So for uniqueness, implies that y must be, or y not, so I apologize for that. So y not which is the same as y, okay? And where's that? Here, okay? This must be tx. X here is what? In the ball centered at 0 with radius 2, so this is an element of T, bx 0, 2. So let us highlight that one. So y being an element of this, provided that y is in this set. So therefore, what do we have? Therefore, this open ball is a subset of this image. And if you can recognize, this is our claim. Or the one equivalent to it. And yes, according to this part here, okay, this claim and the previous lemma with delta equal to this psi over 2, we deduce the openness of T. So that's the proof of surjectivity implying openness. So the open mapping theorem implies some of the well-known results in functional analysis. The first one is due to Banach. This is the Banach inverse theorem, or sometimes as referred to as the Banach theorem. Okay. So again, we have two Banach spaces x and y. And a bounded linear operator T. If T is bijective, then its inverse is bounded. So we utilize this in in the previous lectures where we have shown that the set of all bijective linear maps forms an open subset of the space of bounded linear operators. So for bounded linear operators, if you have a bijective map, then the inverse is also bounded. So from a linear algebra, note that the inverse is linear. Okay. So if your linear map is a bijective, then the inverse is also linear, and you can easily show this observation here. By the open mapping theorem, okay, for each V open in, I should say open in X, okay, So we take here an open set in X, and we want to show that the inverse image of the inverse is open in Y. However, first, by the open mapping theorem, if V is open in X, T of V is open in Y. But of course, this is what? The inverse image of T inverse at V. So the inverse image of an open set in X is open in Y. Thus, T inverse is continuous. By the definition of continuity for general topological spaces. That is, the inverse image of open sets in the codomain or open sets in the domain. So we have a linear and continuous operator. Hence, this linear operator is also bounded. And that's the proof. And from this Banach inverse theorem, we also get the so-called closed graph theorem. So we say that, okay, first, we consider again Banach spaces X and Y, and T to be bounded from X to Y. Then T is a bounded linear operator. Wait. So that's superfluous. Let us assume that this is linear. Okay. Then T is bounded if and only if the graph of T is closed in X. In other words, T is closed. T is closed. That is the graph of T. So what is the graph of T? This is the pair of points x dx. Okay, is closed in the topology or the product topology x cross y. So you can show that in fact these are equivalent. A map that sends closed sets into closed sets is equivalent to the closeness of the graph. Okay. So for a linear operator between Banach spaces, boundedness is equivalent to the closeness of the operator, or equivalently, the closeness of the graph. So to visualize that one, for instance, this is our space X, and this is our space Y. And let us illustrate this graph of T to be in this way for a point X, and we have here a point Tx. So this graph is just the set of ordered pairs X Tx. And continuity, is equivalent to the closeness of this graph in this product space X cross Y. So X here would be the horizontal and Y would be the vertical. So this would be the product space, the rectangle, if you like. Okay, so let us look at the proof. There are two directions. So let's start with this one. Okay. Let T be bounded, linear and bounded. Suppose that I have a sequence in the graph. So in other words, must be of this form that tends to some ordered pair xy in the product space. So here we would like to show that the limit must be in the graph. Then, okay, you can show that the product, okay, space is a Banach space under the norm or with respect to this product norm. So we need some space. This is equal to, okay, there are several ways, but let's say, let us take this one. Okay. So with this norm, product norm, you can easily show that xn tends to x in capital X, and txn tends to y in capital Y. Continuity of your linear operator T implies, okay, that txn tends to tx in Y. Hence, the uniqueness of limits in Y implies that Y is equal to tx. Thus, we can say that xy is equal to x comma tx, and this is in the graph of T. So therefore, the graph of T is closed in x cross y. And we establish one direction. So for the reverse direction, let us go back to this figure here. So suppose that the graph of T is closed in x cross y, hence a Banach space with respect to the inherited norm. So we know that a closed subspace of a Banach space is again a Banach space. So we write a T, okay, as a composition of two maps. So first, let us send a disordered pair, okay, by a projection on X. Okay, and we can send also this So this is the same. Let's say, let us define this to be pi y x dx. So define two operators, pi x and pi y, on the graph. So this sends the first coordinate, and this sends the second coordinate. So in other words, pi x of x dx is x, and pi y x dx is equal to t of x. Okay. Then you can immediately show that pi x and pi y are linear. Okay. So this map is linear, or these maps are linear and bounded. Also, pi x is invertible. So you can use the fact that t is a function. Okay, so a point on the graph corresponds to a unique point x with respect to its projection on capital X. Okay. By the Banach inverse theorem, okay, pi sub x inverse is a bounded linear operator from x, the graph of t. Okay. Take note that from the first one, we already know that this is a bounded linear operator from the graph to y. So this one here, okay? Now this is sufficient since, okay, take note that t is what? T is basically the composition of these two projections. More precisely, you take the inverse of the projection of x, and then you compose this with pi y to get a t. So instead of sending x to tx directly, we go to the graph first. So here, t is the composition of the inverse of the projection onto the x component, and then followed by the projection onto the y component. The composition of two continuous mappings are continuous. Composition of two linear maps is again linear. Therefore, this is linear and continuous. Hence, this is an element of a bounded linear operator from. So you start here, go here intermediately, and then go to y. Okay, and I think that's the reverse direction. So the graph of t is closed in the product space will imply that t is a bounded operator, provided that, of course, it is a linear. So let me close this lecture by stating some consequences. Consequence of the Banach inverse theorem. This is the so-called closed range theorem. So I will not state here the precise formulation. But the main idea is this will generalize, okay, under some conditions, of course. The known fact in linear in linear algebra, wherein the kernel or the nullity of a matrix transpose is the same. I should say the nullity of A is the same as the range of the transpose, the orthogonal complement of the range transpose, and similarly the nullity of or the null space of the I should, of course, these are all equivalent in finite dimensions, but let me present to you the precise formulation. Okay, and here the orthogonal complement of the nullity transpose is the same as the range of null space, I should say, is the same as the range of A for n by n matrices. So here, of course, one has to consider, let's say, the case of Hilbert spaces, for instance. So the orthogonal complement is well defined, and one should define the transpose of an operator, and that is what we call the dual. So the closed range theorem aims to generalize under certain conditions this property in the case of matrices. Here, under some conditions, because this is not true for infinite dimensions in general. This closed range theorem can be used to prove the Banach-Netschas-Babushka theorem. And we illustrated this an application in terms of the heat equation. And moreover, it can be shown that this will imply the so-called Bretsy splitting theorem. So the aim of this theorem is to solve the infinite dimensional version of, let's say, the following problem called a saddle point problem. So let me state this in the case of matrices. So let's say if you have A, B transpose as 0, this is a 0 matrix B, let's say U and P, FG. Here, the given data is the matrix A, which is, let's say, an n by n. B is also a square matrix. F is a vector in Rn. G is a vector in Rm. Okay. Aha. So this should not be a square matrix. So this must be in what? Rm by n. Or I should say the other way around. And therefore, the unknown here is a vector u in Rn and p in Rm. Okay, so this does not make a sense. I think we need to have here b 0. And this must be replaced by, okay, m by n. So the dimensions now makes sense. So here it is called a saddle point problem because this matrix may have a negative eigenvalues and a positive eigenvalues. So this, in contrast to, let's say, the Banach-Netras or the Lax-Milgram theorem, where the eigenvalues are all positive. Here you can have a negative eigenvalues. Such infinite dimensional version appears, let's say, in, for instance, the mixed formulation of your Poisson equation, where u is the let's say this. So u is the heat flux, say temperature, and P is the heat flux. And it should be the other way around. Okay. And for the Stokes equation, appearing in a steady fluid dynamics, for instance, where P is the pressure and U is the fluid velocity. So the close range theorem again, which is a consequence of the Banach inverse theorem, gives rise to these two theorems, the BNB theorem and the Bretzi splitting theorem. So as I said, we already know an application of the BNB theorem by the heat equation. On the other hand, for the Bretzi splitting theorem, this can be applied to infinite dimensional saddle point problems wherein the Poisson equation can be written as a mixed formulation, mixed in terms of the temperature and the heat flux, and as well as in the case of steady fluid flow. where you have the Stokes equation as a simplified model, where P refers to the pressure and U as the fluid velocity. Well, these ideas can be utilized again to establish the existence and uniqueness of solutions, and using so-called finite element method, we can even determine approximations of these problems. Okay. Because we have a limited time, we do not discuss in detail these applications, but for those who are interested in looking at the proof of how the Banach inverse theorem implies this closed range theorem, and later the breadth splitting theorem, I will include that in the lecture notes. So that's it for the consequences of the Baire category theorem. And in the succeeding lecture, we will discuss the weak and weak star topologies. So see you then.